Allow me take you through chemistry practical, the year 2012. This is the year we did our this is my paper. I did this paper at this hour. I was in class doing this paper. It was on Wednesday, 31st 10th 2012. Let us go inside and see how it was looking like. You are provided with solution A containing an oxidizing agent A, solution B containing 0.05 molar aqueous sodium thiosulfate, solution C containing a reducing agent C, aqueous potassium iodide, solution D starch solution. You are required to determine the concentration of solution A, the rate of reaction between the oxidizing agent A and the reducing agent C. So procedure 1, the titration part of it. Using a pipette and a pipette filler, place 25 centimeters cube of solution A into a 250 ml conical flask. Measure 10 centimeters cube of aqueous potassium iodide and add it to solution A in the conical flask. Shake the mixture. Add 10 centimeters cube of 2 molar sulfuric acid to the mixture and shake. As you can see, practical is following instructions. Fill the puree with solution B and use it to titrate the mixture in the conical flask until it just turns orange yellow. Add 2 centimeters cube of solution D to the mixture in the conical flask. Shake thoroughly. Continue titrating until the mixture just turns colorless. Record your salt below. Repeat the procedure and complete this. Retain the remainder of solution A and solution D for use in the procedure 2. So this was the table, and the table is already filled for us. Here we are using 2 decimal places. Like I told you in the previous videos, you can use 1 decimal place or 2 decimal places allowed. So here we have filled our table with the 2 decimal places. So calculate the average volume of solution B. So solution B we know very well. It is important for you to understand what is solution B. Solution B is sodium thiosulfate, 0.005 molar. So there is so many information which is here. You may not understand some things, but following instructions and doing what is required, you will see that you don't need to know what is happening in this procedure. You don't need to know why that we are using so many reagents, mixing what and what. You don't need to know that. Yours is to follow instructions, and then so you can find that you can see that this information, too much information is not important. The only thing is, did you follow the instructions? Simple and clear. Calculate the average volume of solution B. The average volume solution B used is 15.35 plus 15.45 plus 15.45 divided by 3. This one is giving us 15.42 centimeters cube, and that is our average. Calculate the number of moles of sodium thiosulfate. Remember, sodium thiosulfate is solution B. Solution B. So this is the solution B we have used. So the average volume we have here is solution B, sodium thiosulfate. So we are asked you to calculate the number of moles of the solution that we used. Number of moles of sodium thiosulfate B, solution B used. But we know here, from here, what we are provided that 0.5. We know from here that 0.05 molar is the number of moles in 1,000 of sodium thiosulfate. So we use that information and say 0.05 is the number. In fact, capital M stands for molarity, and the molarity simply is the number of moles in 1 liter. So 0.5, this simply means that it is in 0 0.05 is the number of moles found in 1,000 centimeters cube of solution B. So we will ask what will be the number of moles of 15.42 centimeters cube of B, the one that we used. What will be the number of moles? So here it is 15.42 times 0.05 divided by 1,000, and this one will give us 0.0000771 moles. Given that the mole ratio of A reacts with 6 moles of sodium thiosulfate, calculate the number of moles of A that were used. That's the thing. The only thing you need to understand is that A reacted with B and you have been given the mole ratio. Other things, you don't bother them. So the knowledge you have how to use the mole ratio is what is important. Now A is reacting with B. We know B is sodium thiosulfate. Sodium thiosulfate. B is sodium thiosulfate. We have already calculated the number of moles of sodium thiosulfate that reacted with 25. This one was 25 centimeters cube. This one was 15. We have calculated the number of moles. We know the number of moles of this is 0. First, we have been given the ratio that 1 mole, so 1 to 6. 6 moles of sodium thiosulfate reacted. So, but we know the number of moles of B. So the question is, what is the number of moles of A using the ratio? So we will say that 6 moles equal to the moles we have calculated in our previous question. Because this is the number of moles of sodium thiosulfate that was reacted with A, so this 6 is the 6 moles we have been given is the same as this. So we will ask, what about 1? 6 equal to 0.000771 moles. What about 1? So it is 1 times 0.000771 divided by 6, and this is the number of moles of A, which is equal to 0.0001285. That is the number of moles of A. Given that calculated the concentration of solution A in moles per liter. So the only thing you need to know is that what was the volume of A that reacted with B? We pipetted 25 of A, 25 centimeters cube of A. So we know that 25 centimeters cube of A contains this number of moles, equal to 0.000128 moles. Concentration in moles per liter simply means molarity. Molarity is the number of moles in a liter. Moles in a liter. A liter equal to 1,000 centimeters cube. So we would ask 1,000 centimeters cube of A will contain how many moles? So it is 1,000 times 0.0001285 divided by 25. This one is equal to 0.00514 moles. It is molarity, so capital M. Or we can also write as 0.00514 mole per liter. Moles per liter. Qualitative analysis 2012, the year 2012. This was the question 2. I have skipped the other question because it is a question that needs, it is a graph question, rate of reaction, which each student should be able to handle. So that's why I just skip it, because the question, start question of rate of reaction will always vary. But the things we are doing here in qualitative analysis will be always the same. The same information that you need to write here is the same, which that's why I usually emphasize on qualitative analysis and multi-iteration. But for the rate of reaction, it can vary, so you cannot find the exact thing that was there. But this one, if it is sodium chloride, it is sodium sulfate, aqueous sodium sulfate, it is the reagent will be given and the observation will be the same or the other way around. You are provided with solid E. Carry out the experiment below. Write your observations and inference in the spaces provided. Place ore of solid E in a boiling tube. Add about 10 centimeters cube of distilled water and shake until all the solid dissolves. Label the solution as solution E. Use solution E for the experiment Roman 1, experiments Roman 1 to Roman 2. So Roman 1, 2 centimeters cube of solution E in a test tube. In each of the experiment, Roman this to Roman 4, add 2 drops of aqueous sodium sulfate. So we are adding aqueous sodium sulfate. Sodium sulfate, therefore, our observation is that white precipitate is formed. A white PPT is formed. We are adding sodium sulfate. Remember sodium sulfate, the sulfate ion, it means if it finds the lead 2 ions, the carbon, the barium and the calcium, they will form a white precipitate, lead sulfate, barium sulfate and calcium sulfate. So this means that barium 2 positive, comma, lead 2 positive or calcium 2 positive is present. The reason why I'm emphasizing on qualitative analysis is that the next, in this year, for example, you can be given sodium sulfate and there will be no white PPT. If there is no white PPT and you are using sodium sulfate, you will write this and this one absent. You see, this one will not, there's nothing much that will change in this. Add 5 drops of aqueous sodium chloride. We are adding sodium chloride to solution E. So to about 2 centimeter solution E, we are adding 5 drops of aqueous sodium chloride. The observation is that no white precipitate, no white PPT is formed. We expect the chloride to form a white precipitate because sodium, we don't care about it. We are concerned about the chloride. The chloride ion will form a white precipitate with silver, with lead, right? But from our previous, we don't have silver. So we are not going to include silver because that one will be called contradictory response or answer. Therefore, it means if there is no white PPT, it means the lead we thought that was present here is absent. Lead is absent. Lead is absent. So if in our previous we had barium, calcium and lead, now lead is absent, then what is present? It means that barium from this and calcium, 2 ions are present. That's what it means. But this one is correct also. You can just write lead to absent. It's accepted. To about 2 centimeters cube of solution E, add 2 drops of barium nitrate. Barium nitrate, no white PPT, no white precipitate. We are adding barium nitrate If there is no a white precipitate, barium forms a white precipitate with the sulfate, with the sulfite, and the carbonate. But there is no white precipitate. It means that the sulfate, the sulfite, and the carbonate are absent. Are absent. That's what it means. To 2 centimeters cube of solution E, add 2 drops of lead 2 nitrate. Now we are adding lead, right? What is observed? No white PPT. No white PPT. So lead will form a white precipitate with chlorine. Lead will form a white precipitate with a sulfate, with a sulfite, with a carbonate, and the chloride. Red chloride is a white precipitate. Red sulfate, red sulfite, red carbonate is a white precipitate. But from our here we said sulfate, sulfite, and this one is absent. And yet there is no white PPT. We are not going to repeat this one. Therefore, it means that the chloride ions are absent. Only we are not going to write this one, any of the carbonate or sulfate or this, because in the previous Roman 3 we said this one is absent. You don't repeat it here. If you repeat, it is considered a contradiction kind of answer. To 2 centimeters of solution E in a test tube, add 5 drops of aqueous sodium hydroxide. Sodium hydroxide. Add the piece of aluminium foil provided to the mixture and shake. Warm the mixture and test any gas produced with both blue and red litmus paper. So, probably this is the first time you are hearing. We have never come across aluminium foil used in qualitative analysis, in organic qualitative analysis. But it was there 2012. So if you have not seen this paper up to this moment, you don't need to be shocked. Aluminium foil is always sometimes used with sodium hydroxide. So we want to check the observation that is made. So this is 2012. We did that and we got it. Warm the mixture and test any gas produced with both blue and red litmus paper. So we are using red and blue litmus paper. So what is the observation when you are mixing sodium hydroxide with aluminum foil and then heat? What is observed? Effervescence first occurs because a gas is produced. Effervescence occurs, a colorless gas is produced. A colorless gas colorless gas produced. A colorless gas is produced. And then what would happen to the litmus paper? Blue, red, change red litmus paper, red litmus paper changes to blue. Red litmus paper changes to blue, and then blue remains blue. Blue remains blue. So if effervescence occurs, a colorless gas is produced. So that tells you that is present. For effervescence to occur, a colorless gas is produced. Then inside there now the mixture the reaction went on, and the nitrate ions were present. red litmus paper changing to red litmus paper changing to blue, it means inside there a basic gas was produced, and the basic gas, the only basic gas we know is ammonium ion, ammonia gas. So present. So those are the observations and the inferences expected when you have sodium hydroxide reacting with the ammonium foil when warmed, and then the gases tested using litmus papers. We are provided with solid M, a solid F. Solid F, carry out the following tests. Write your observations and inferences provided. Place all solid F in a pouring tube. Add 20 centimeters of distilled water and shake until the salt dissolves. Label the solution F. The first one, we are adding sodium hydrogen carbonate. Then we are burning this one in a Bunsen burner. So you need to know now this one is organic. What we were dealing with previously is inorganic qualitative analysis, and this one is organic. So solution F, now we have solution F. Add about a half of the sodium sodium hydrogen carbonate provided to 2 centimeters cube of solution F. Whenever you are adding sodium hydrogen carbonate, expect effervescence or no effervescence. So here there was no effervescence. If the word effervescence becomes difficult for you to write no fizzing. If fizzing comes difficult, write no bubbles produced. No bubbles produced. So if that happens, it simply tells you that the organic acids, alkanoic acids, is absent. No effervescence, it is the alkanoic acid which is absent. Add about 10 centimeters cube of the dilute hydrochloric acid to the rest of solution F in the pouring tube. Filter the mixture. Wash the residue with about 2 centimeters cube of distilled water. Dry the residue between filter papers. Place about 1/3 of the dry residue on a metallic spatula and burn it in a Bunsen burner flame. So it burns with a sooty yellow flame. It burns with a yellow sooty, yellow flame, smoky flame. All those are correct answers. It burns with a smoky flame, sooty flame. So if it burns with a yellow flame producing a lot of smoke, then it means the unsaturated organic compound are present. Unsaturated organic compound. Or you write the double bond, triple bond present. Place all the remaining residue into a pouring tube. Add about 10 centimeters cube of distilled water and shake thoroughly. Retain the mixture for test in C. So here we want to see or to observe whether the residue dissolved in water or not. So the residue, some white suspension was formed. Or the solid did not dissolve, remains undissolved. Remember, for a solid to be called that it is soluble in water, it must form a colorless solution. But if it forms a white, some white suspension, white things, then it means it is not soluble in water. It is not completely soluble in water. So we can say here the solid is non-polar. You can also say that a compound is slightly soluble. Partially. Compound is partially soluble in water. Partially soluble in water. Divide the mixture into two portions. To the first portion, add the rest of the solid sodium hydrogen carbonate. So we are adding sodium hydrogen carbonate. Always expect effervescence or no effervescence when you are using sodium hydrogen carbonate. So this time around here there is effervescence. Effervescence occurs and a colorless gas produced. Or you can say fizzing occurs. So if fizzing occurs, it means that this is present. The alkanoic acid, this is the functional group of alkanoic acids, is present. To the second portion, add 2 drops of bromine water. Bromine water is yellow. We expect for it to be decolorized. We expect it to be decolorized if there is an alkene or an alkyne. But if it remains the yellow color remains, then it means the double bond, triple bond is absent. So we can say for this one, bromine water is not decolorized, meaning that the yellow color, meaning that the yellow color of bromine remains yellow. The color is retained, so that what it means is that this one, the double bond or the triple bond, is absent. I want to thank you for your time. Also share this information to your friends and comment. Just like, it's just a click, please.